Hello everyone and welcome. We are so happy to see you. We are the Lambdas and today in this video we are going to be modeling IED blasts using differential equations. Let's get started. So, first, what is an IED? Well, IED stands for an improvised explosive device. It is made to destroy. IEDs can come in many shapes and sizes as you can see in the picture on the screen. All IED consists of an initiator, a switch, a main charge, and a power source. They can generally be found beneath the ground or implanted in vehicles. More specifically, IEDs can contain materials such as glass, nails, and metal fragments designed to increase the amount of objects propelled by the explosion. As you can see in the chart, here are the different types of IEDs used in the past terrorist attacks around the world. Here is a video breakdown where it visually represents what an IED is.
Locked and loaded, 2nd platoon rolls out. They're traveling 30 miles west on the paved A1 highway before they turn off onto a dirt supply route that's littered with buried bombs.
That's what I like to hear. Let's get this.
Outside the walls of the base, the slow-moving convoy is dangerously exposed. This is the Taliban's home turf, and the insurgent fighters are everywhere. But they don't wear a uniform. Blake and his men are a tempting target for roadside bombs. Sniper fire, rocket-propelled grenades, and suicide bombers.
1126 is getting ready to turn off.
30 miles west of the base, 2nd platoon is leaving the A1 highway, one of the few paved roads in the country.
We're about to go off-road. It's gonna get bumpy.
But bumps are the least of the platoon's problems. The unpaved supply route makes it easy for insurgents to bury homemade bombs. The unit is on high alert.
Since we turned onto this route, we're doing deliberate clearance all the way over there because this is a known spot for victim-operated IEDs.
Most IEDs are made from a few simple parts. A power source, like batteries. A main charge, like homemade explosives. A detonator, to set off the main charge. And a switch, like a pressure plate or tripwire that closes the circuit and triggers the IED.
So, you may be asking yourself, what does an IED have anything to do with differential equation? Well, as you know, there are many military soldiers, no matter what country they're from in the field, who are constantly facing IEDs day to day. What differential equations does for them is that it can be used to calculate the types of bombs being used and the after effect of them on soldiers. With this information, many injuries can be avoided and lives saved. To better understand the correlation between IED blasts and differential equations, we used a SIMIODE document as a guide. Now, imagine driving over an IED. What do you think could go wrong? Well, for starters, you'd be in the air immediately. Due to the strength of the explosion, the vehicle would propel in the air. As you can assume, this is extremely dangerous and in many cases cause serious injuries and death. Because of this, the US government has adjusted their vehicles by making them more armored, which can reduce the amount of damage caused. After many trial and errors, it was found that the size of the vehicle had a big impact on the amount of damage that a passenger can sustain during an IED blast. So to recap, the higher the mass of the vehicle, the less damage would occur. Thanks to vehicle modification, vehicles are now more armored. While they may not be able to keep the passenger 100% safe, it does increase their chance of survival. As you can see, here's a chart that can demonstrate where an IED can be placed, how much it would weigh, and the distance needed to evacuate from the object to be safe.
Like mentioned earlier, The military has developed a MIL STD 1472G to help prevent head trauma that has occurred during IED explosions. The head trauma usually happens because of the rapid acceleration and deceleration that the vehicle and passengers within experience after driving over a bomb. For example, if you're in a vehicle without blast-resistant seats and drove over an IED, you would most likely be accelerated upward due to the force of the bomb. This may not seem like a big deal, but it also means that your internal organs, including your brain, are subject to acceleration. Put it this way, if you were to put a glass inside a metal box and shake it around real fast, when you open up that metal box, the glass would be broken. Think of that as your brain inside your skull, and that's what would happen during an IED explosion. It is also worth noting that based on where you're sitting in the vehicle when it is hit by the IED may greatly change how you are affected by it. For example, if you're seated right above the bomb where it explodes, you're far more likely to experience severe damage as opposed to someone that may be seated further away from the side of the impact. When designing blast-resistant seats, the military's main concern was the safety for the passengers inside the vehicle that was hit by the IED. One way in which these seats provide safety to the passengers is that they're able to better dampen the force of the explosion. There are three different types of dampening systems: overdamped, critically damped, and underdamped. Overdamped systems move slowly toward equilibrium. An underdamped system moves quickly towards equilibrium but will oscillate about the equilibrium point as it does so. A critically damped system moves as quick as possible toward equilibrium without oscillating about the equilibrium, as shown in the graph above. Dampening is in the process in which an oscillating system is affected in order to prevent the system from oscillating. In the case of an IED explosion, a non-blast resistant seat would likely bounce up and down multiple times very quickly as a result of the explosion. A blast-resistant seat is able to dampen and absorb these oscillations, which will prevent the seat from bouncing up and down rapidly, which will greatly decrease the odds of sustaining severe injury to internal organs.
When a blast occurs, the acceleration and velocity applied goes up. However, because of a blast-resistant seat, the motion and seat of the passenger comes down during the absorbed blast. This is because a blast-resistant seat is effectively a spring dampener in a car, designed to protect its occupants. It functions as a spring or seat compresses the energy that is stored from that is released, causing it to not bounce as much and bring it back to a more stable state. The vector force equals the mass times the change in velocity over change in time. Because of the dampeners, it increases the time a force is applied. For example, as an MRAP vehicle drives over an IED, upon the explosion, the spring dampers inside the car spread the force over a period of time, causing less serious injuries to the occupants inside. To visualize the blast-resistant effectiveness, here's a graph conducted by the testing on Hybrid 3 test dummies and the MIL STD 1472G vehicle. This is done to show the difference between a vehicle that had unattenuated and attenuated seats. The vehicle itself in an IED blast suffers a great amount of damage. However, the most important thing in this situation is to protect the occupants inside. When a seat is unattenuated, which does not have the shock absorbers to their most capacity, the amount of force is much greater than an attenuated seat. This is the difference between a life and death situation for the occupants. This is very important, not only military applications, but in the real world as well. Every vehicle has shock absorbers that absorb impacts from the ground to make sure the occupants inside are in a safer position. From depicting this graph, the importance of acceleration over time is very meaningful when extracting data using shock absorbers. Knowing that the acceleration over time is greater means a greater risk for its occupants. Manufacturers designing these shocks must take into account the safety of the passengers. From this data, it clearly shows the importance of shock absorbers in a military application.
On this slide, we explain background information on differential equations. This is important so that we can understand what differential equations are so that we can then create a proper differential equation which can be used to model real-world scenarios such as IED blast. So a differential equation is an equation which contains one or more terms in the derivatives of one variable with respect to another variable. It's pretty much one way of saying that the rate of change of a variable and the rate of change of another variable is then connected through the differential equation, which draws a relationship between these two. So in this scenario in IED BLAST, it's important to consider different variables so that you can create a proper differential equation which will include all these variables, which would then make it a more accurate equation. So one variable that has to be considered is the vertical displacement caused by the explosion. This is pretty much just another way of saying that when you roll over the IED, how high the vehicle would fly in the sky after the explosion. The duration of the explosion, this is important to consider because one bomb that would be going off for longer would obviously cause more damage as opposed to one that wouldn't. The amount of force created by the IED, this is important because an IED that creates a greater force than another one would cause more damage as opposed to the other. Acceleration function, this is important and it connects back to the vertical displacement because after you roll over the IED in the vehicle would then quickly accelerate into the sky and then decelerate back towards the ground. The mass of the vehicle, this is important because a vehicle of lesser mass would be affected differently by an IED blast as opposed to another one. The mass of a passenger, this is also similar to the mass of a vehicle because somebody that weighs less or more would be affected differently in the event of an IED blast. In this scenario, an IED recovered creates a force of 100 kilograms times centimeters over meters per second squared within 20 milliseconds. This impact would result in sustained damage not only to the cabin of the vehicle but also the occupants side of it. A measure of potential head trauma injuries is based on the head injury criterion, also known as the HIC, which is the differential equation that we have here. Measured in milliseconds of this metric, an HIC of more than 600 declares there is a risk of head injury. So it's pretty much one way of saying that if you solve this differential equation and the value at the end would be higher than 600, you know that the person involved in the IED blast would be at a more likely risk of head injury. So on this slide, we explain what the acceleration function is in this HIC differential equation. In this equation, you can see that the acceleration function is just a of t. However, you can't solve this equation with just a of t being there. You need to actually know what the variables are inside of the acceleration function, which is explained here. So the acceleration function can be described as mg minus drag coefficient times the vertical displacement. So pretty much the mass times gravity times or minus the drag coefficient times the vertical displacement. You put all this together and then you sub that in for a of t here so that you can then solve this equation. Without those four variables, you wouldn't be able to properly solve this equation because you would be leaving out a lot of variables which would obviously affect the person in the blast. However, that equation is not the only thing that would describe the possible trauma that can be caused from a IED blast. It's also important to consider the energy that would be transferred to the human brain from the IED blast. An IED blast would likely cause a lot of energy and heat energy, which would then be transferred into the person. And then after the energy has entered the brain, the energy becomes to rapidly decay exponentially, which can be represented by this equation. So this equation is just an exponential decay equation, which pretty much explains what happens to energy after it enters the brain in the event of an IED blast. This is important so that we can model and we can understand how much energy would be transferring into a person's brain, because energy above a certain amount would obviously cause potential severe brain injury.
Alright guys, now let's go into some of the health effects when encountering an IED. First and foremost, we have overpressure damage. This is caused to the lungs, the ears, the abdomen, and other pressure-sensitive organs. For example, there's blast lung injury, which is caused by the extreme pressure of an explosion. And unfortunately, this is the leading cause of illnesses and death for initial survivors of an explosion. Next, we have fragmentation injuries. This is caused by objects thrown by the blast. So some of these objects are like from the bomb or the flying debris. But regardless, that penetrates the body and can actually cause a lot of damage to it. Next, we have impact injuries, which are caused by the blast when it throws a victim into another object. Some of these injuries include, but are not limited to, fractures, amputations, and trauma to the head and neck. Finally, there's thermal injuries, which is caused by burns that seep through the skin, the mouth, and the lungs. In case if you're not aware of some of these IED attacks, here are some examples. There was the Madrid train attacks, which consisted of 10 explosions that rocked through 4 commuter trains during rush hour. And there was this Olympic Park bombing, which took place during the Olympics in 1996. This is where an IED that was composed of pipe bombs was hidden in a backpack, and this backpack exploded in the Centennial Olympic Park in Atlanta, Georgia, which is where the Olympics were hosted at the time. Now, if you find yourself in the event that there is an IED attack, here are some of the best ways given by professionals about what to do. First and foremost, being aware of your surroundings is the absolute best way to protect yourself and others from an IED attack. Yes, advanced technologies help police and other authorities when it comes to these threats, but an even more effective way is to encourage others to be on the lookout. I like to think of that saying, if you see something, say something. Next, if you are at the immediate site of the IED attack, your top priority must be to get out of that area. This will increase your safety, and most times there will be a secondary device present in that area. So by doing so, you will reduce your exposure to that dust, that smoke, or any hazardous substances that could result from the IED blast. Lastly, if you are near but not at the immediate site of attack, please avoid being in that area. I know that when there's a big commotion, a big scene going on, it can be so easy to get caught up and find out what's going on. However, this is the most dangerous thing that you can do for yourself. So please, 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 if you can, if there's authorities, listen and obey to them. And if you can, stay away from windows and doors. Now, I know that this topic is very sensitive and it can be very overwhelming. So I have a funny joke for you in the next slides to, ease it up a bit.
Being in a situation involving an IED can be very dangerous. To conclude, an IED stands for Improvised Explosive Device. It's a homemade explosive used to disarm and destroy. Using differential equations, we can model these IED blasts mathematically. This is important because it can provide information to the military about what bombs are being used and the data that can be extracted to help prevent injuries and save the lives of many people. After going through this presentation, you should be able to answer the following questions. How does a blast-resistant seat impact the amount of force applied to occupants? Where else are shock absorbers applied in the real world? And why is it important to have shock absorbers in general?
Alright guys, here is your joke of the day. So why did I divide sine by tan? I'll give you a little bit of time to think about it. Did you get it? Just 'cause.